going to go over hypothesis testing with the single sample t. So I've given an example here talking about children in preschool given a standardized language test. It shows the population mean is 50, if you see here, 50. And there's a sample of preschool children that scored the following: 53, 61, 49, 56, 62. So we know that n equals 5, right? Our sample size is 5. Now it says it wants us to test whether preschoolers' language scores are better than average children. And they want us to test this at 0.05. So basically, is what's saying is children who are in preschool, we're assuming that they are going to have better language skills than the average child. So we're going to go ahead and walk through all the steps of testing this. So we know it's alpha 0.05, and we're wondering whether preschoolers' language scores are better than average children. So at 0.05, and talking about it being better than average, if we look at the word better, that means we're doing a one-tell test. So we're going to look at step 1. The first thing so step 1 is we want to state our hypotheses. That's both hypotheses. So the null is what we are trying to reject. So basically this is going to state preschoolers, let's say preschoolers' language skills, language scores are not significantly better than the average child. If you'll notice, this is the statement that it's not going to differ. And because we're looking for an increase, we're not going to say anything different. We're just going to say it's not going to increase or it's not going to be better. We're not going to make any assumptions about it going the opposite direction or anything like that. We're just going to use the standard hypothesis and throw in the word not. And then our alternative is basically that something will happen, that they will be better. So preschoolers' language, and this can be time consuming, but this is important for setting up your criteria, are significantly, and I usually abbreviate, significantly better, that's just for time's sake, than the average child Bam, so we have our null and we have our alternative. So now we can move to step 2. I always say state your hypotheses before doing any calculations or setting up your criteria. That way you know what you're looking for and you know whether you're doing a one-tell or two-tell, and that's all in stating your hypothesis, which is going to determine that. So step 2 is several parts. Step 2, we need to find our degrees of freedom, which we know degrees of freedom equals n minus 1, right? So we know in this case degrees of freedom equals 4 because we have 5 scores. Here's those original scores, 5. And now we're going to have to look up in our T distribution table, which is at the back of your textbook in table B2, and in that left column that says degrees of freedom, you find the degrees of freedom of 4. Now be very careful. Remember, we have alpha level 0.05 and we're using one tell. So because we're looking at scores to be better, we're going to use a positive. So when you look in this, make sure you're looking under the column that says proportion in one tell. Remember, our alpha was 0.05, and we're going to look down, and if you'll notice, your critical T that you should be getting is 2.132 in the column for 0.05 one tell. So our answer is 2. 5.132. And that's a positive, so you can just leave it. Don't put any signs in front of it because this is your 1-tel critical value for degrees of freedom of 4, looking for scores to increase. Now we need to move to step 3, which is all parts. So I have them listed. We're going to calculate the t-statistic. Then we're going to calculate an effect size, and then we'll calculate a confidence interval. This is all part of testing the statistic. So the first thing we'll do is our step 1 of that step 3 component, and we will calculate the t-statistic. So here we have the original scores, and we have our equation, sample mean minus population mean divided by the estimated standard error. Now if you remember, going all the way back, I'll go back to the very beginning, our population mean was 50. So we can go back to our steps here, and we know mu equals 50, right? So we're going to have to start from scratch. We have a raw data set. So the first thing I start doing is just getting the information I need to be able to calculate my test statistic. So the first thing I'm going to do is I'm going to get sum of x, then I'm going to get sum of x squared. Remember, sum of x squared without the parentheses around it is basically each score individually squared and then added. So if you get your sum of x, which is 53 plus 61 plus 49 plus 56 plus 62, that's 281. If you go through and add up the x squared, so 53 squared plus 61 squared plus 49 squared plus 56 squared plus 62 squared, you get 15,911. Now, we have everything we need at this point to obtain our mean and our estimated standard error. So obviously we know to calculate the mean, we're going to take our 5 scores, add them up, the 281, and divide that by your sample size. So our M for this is 56.2. So that is our sample mean. Now we need to get a sums of squares so that we can get our standard deviation and then use that to get our standard error. So if you remember, sums of square is the sum of x squared minus sum of x total squared divided by n. So we're going to just plug in our sum of x squared, 15,911 minus 281 squared divided by 5. Once you calculate that out, you should get 118.80 as a sums of square. So now we can get our standard deviation. Standard deviation, if you remember, is sums of square divided by n minus 1, that's our sample standard deviation, all with the square root. So we're going to have 118.80 divided by 4. Take the square root of all of that, and if you calculate that out, you should be getting 5.449, and I'm going to round to 8. I would recommend keeping 4 decimals, rounding appropriately at the 4th decimal from now on, all the way through your calculations until you get to your final calculation, and then you can round to 2 decimals for more accuracy. So now we can use that standard deviation to get the estimated standard error. And if you remember, that is the standard deviation of the sample divided by the square root of n. So we have 5.449 2.4498 divided by the square root of 5. If you calculate that out, you should get 2.4372 is that standard error. Now we have everything we need to calculate our t-test. So I'm going to just give myself a tiny bit more room here, hopefully. Try to get some room. So we have 56.2, that is a decimal, minus 50, right? Sample mean minus population mean divided by 2.4372. So be careful that you're not getting your sample mean and your population mean mixed up, because if you do, and you put 50 minus 56.2 instead of 56.2 minus 50, your t ends up coming out the opposite direction that it should. That's a problem, because that's telling us the opposite, and that would be telling us that we had a type 3 error when we really don't. So our final t equals 2.544. This is our t obtained. This is the first of our steps for calculating the test statistic. So that was the t statistic, but we have more to do. So we got a t obtained of 2.544. Now we need to calculate an effect size, and we need to calculate our eta squared, because those are two different effect sizes, and I'm going to go ahead and calculate both of them so that you can get practice. And we'll also have to calculate a confidence interval. So we'll move forward, more room, and we'll look at our effect size. So if you remember, our sample mean was 56.2, our population mean is 50, and we're going to divide that by the standard deviation, not the standard error. So the standard deviation, if you recall, look here. Here we have the standard deviation 5.4498. So we're going to plug in 5.4498. Now, we always want to take the absolute value of Cohen's d. We report it as a positive, even if it's a negative. In this case, it wouldn't be, but it's always reported as a positive. If we calculate that out, I end up with 1.14. Now, let's calculate our eta squared, just so that we can practice both. If you remember, eta squared is the t obtained squared. So if you remember, our t obtained was 2.544. We're going to square that, all divided by 2.544 squared, plus our degrees of freedom. Remember, our sample size was 5, so our degrees of freedom is 4. When you plug this into the calculator, I suggest putting parentheses around this denominator. Otherwise, you will come up with a different answer, the wrong answer. So once you calculate that, you should potentially be getting eta squared is 0.618, which I would round to 0.62 officially. So now we have our effect sizes. We only need to report one of those, but I want you to learn how to do at least eta squared and Cohen's d. We're going to move forward and calculate our confidence interval now. So remember, our confidence interval is calculating the lower and the upper boundaries with which is what we're estimating the population means would fall within, that lower and upper. So even though our original hypothesis is one-tailed, we need to look up a two-tailed t-crit, because this t right here is a critical value. And because confidence intervals include the lower and upper boundary, we need to look that up as a two-tailed rather than utilizing the one-tailed t-crit that we had before. So we plug in, if we look up the critical T value of degrees of freedom 0.05, or degrees of freedom 4 with an alpha level 0.05, because now we're going to use a 95% confidence interval, because you take 5%, which is 0.05, from 100%, then you get 95%. And we're going to look that up, and you should be finding your critical value is 2.776 with the alpha level of 0.05. So our equation ends up being our sample mean, 56.2, plus 2.776, and then we're going to plug in our estimated standard error that we calculated. And if you look back, it's 2.4372. So this would be our upper boundary. And we're going to calculate that out. And the upper boundary is 62.97. Then if you look at our lower boundary, it's 56.2 minus 2.776 times 2.4372. Same equation, you're just accounting for the negative now, that negative interval. That will give us our lower boundary. The lower boundary should be 49.43 is what you should be getting. So now we have the confidence interval. So now we need to determine whether the test is significant or not. So if you go back and you look at the T obtained, put right here, so here's our distribution, and if you remember our critical value, originally that one held was 2.132, right? So anything that falls over here is significant. Well, our T obtained was 2.544, which is probably over here somewhere. So 2.544 was our T obtained. So it is significant. So now we can state our results. So because this is significant, I'm basically going to restate my alternative statement. So if you go back to the statements, the alternative was that preschoolers' language scores are significantly better than the average child. So I'm basically going to write that in my statistics. So preschool children did have significantly better language scores than the average child as, now we're going to go our T, degrees of freedom in the parentheses, our T obtained, which is 2.544. We're going to have our P related to alpha. We know that because this is significant, P is less than alpha, which was 0.05, 1/10, with, and I'm going to report Cohen's d instead of eta squared. It doesn't really matter. You can report either one, but in this case I'm going to report Cohen's d, with Cohen's d equaling 1.14, and we calculated our 95% confidence interval, 95% CI, and then in our brackets you put your lower boundary, 49.43, comma, and then your upper boundary, 62.97. So there is the APA statement, APA result. It has to be in that format exactly. if you'll notice, some key factors that is very important. We have basically our dependent variable, which is language scores, and we have our independent variable. We're looking at the difference between preschool children and average children. Those are our groups. And we also have direction, and we're stating better. Or if it wasn't, it'd be different. And then we have our T obtained, our degrees of freedom in parentheses, our P related to alpha. We tell whether it's 1 or 2 tell. We have an effect size, and we also have our confidence interval, which is used for t-tests. So now that we've walked through the steps of hypothesis testing, you can actually work on your hybrid that is in Canvas and utilize this as a resource if you get stuck, and go through all the steps and make sure that you don't miss anything, and double check to make sure that your APA result is accurate utilizing this hybrid video. Thank you.